All right, in 1.3.2, we're talking about standard deviation. Standard deviation is a measure of spread. So it tells us how spread out the data in a distribution are. So basically, we have a few measures of center that we use. So a mean is a measure of center, a median is also a measure of center, and a few different measures of spread. So range, IQR, and now standard deviation. Remember when we talked about these things last time, we were talking about whether or not these measures were resistant to outliers. So standard deviation, let's break down the words themselves. And standard means typical. Deviation kind of means distance. So deviation from what, you might ask? Well, it happens to be the deviation from the mean. So when you interpret standard deviation, you can think of it as typical distance to the mean. So the mean is inherent, it's implicit in the formula for standard deviation. But with that in mind, remember that the mean is not a resistant measure of center, so standard deviation is also not resistant to outliers. So at this point, if you're deciding on what measures to use to talk about your data set, you need to know if your data set has potential outliers. If it does have potential outliers, you probably don't want to use the mean to describe where the center is, because the mean is highly impacted by the outliers. So it will give whoever you're reporting these things to an idea that the center is in a place where it truly isn't. It's the mean just being pulled up or down by the outliers. So data with lots of extreme values or outliers, you would typically want to use the median to describe its center and maybe the IQR to describe its range or to describe its spread. But as long as it's relatively symmetric data, it's okay to use the mean as a measure of center and the standard deviation as a measure of spread. All right, so before I move away from this, this is the formula for standard deviation. You don't have to have that memorized. If you go into the supplemental button on our homepage, you can find the AP statistics formula sheet and tables. This is what you're given for the AP exam, and it has all these formulas in there for you. So here's the one we went over in 1.3.1. This is just the formula for finding a mean, and here's your formula for finding a standard deviation. So let's break that down real quick. Xi represents just an individual data. So you're taking individual datum, and for each one of those, you are subtracting the mean. That process is called finding the deviation from the mean. So that's each piece of data's deviation from the mean. You're then squaring that. Then once you do that for every piece of data in the set, you add all squared deviations up. We then divide by your data size minus 1. And then we take the square root of it. You're not really going to have to do that by hand. It's not important. Your calculator can do this for you. What you do need to do is be able to understand what comes out of this, and that is a typical deviation to the mean. Now, a standard deviation will have units, and it's the same units as the data. Because we're initially squaring the units, but then we're taking the square root again, which leaves us in the same unit as the data, the same units as the data itself. So I used to make my students, again, do this by hand the first time. I don't really see a point. You have the formula there if you need it, but I'm going to show you how you can utilize your calculator just to access standard deviation much more quickly. So the important thing is that you're able to interpret it. All right, so just to give us a general idea about standard deviation, I like to start with this. How far in the distribution are the values from the mean on average? And this is to give you some idea as to why the formula works this way. Well, you might go, okay, well, they seem, I'll find this distance, that's 1. And these ones, the mean is going to be 4, by the way, in this case, because they're all centered, perfectly symmetrical around x bar equals 4. You can always add all of them up and divide by how many there are if you like, or you can take my word for it. All right, so what are our deviations from the mean? All right, so we have one piece of data that's 1 from the mean. We have 2 pieces of data that are 1, 2 from the mean. Whoops, 1, 2, 2. We have one piece of data that is 3 from the mean. And on this side, we have one piece of data that's -1 from the mean. So I'm just trying to indicate we're going the other direction. We have 2 that are -2 from the mean. We have 1 that's -3 from the mean. So you may go, okay, well, these are all just the deviations from x bar. So you might be tempted just to add them all up and like take their average, divide by how many there are. So divide by 8. The problem is if you add all these up, you get 0. 0 divided by 8 is 0, and now it just looks like our standard deviation should be 0. Well, the only time a standard deviation is 0 is if all your data is the same, meaning it's all one value, and then there's no spread at all. And that's certainly not the case here. So what they do to get around that, right, is they take these deviations and they square them. And so that's going to make all of the negatives now positive. Then we can add them up. Then we can kind of divide by something. Now, they don't actually divide by the number of data. They divide by the number of data minus 1. And there's kind of technical reasons for that that are beyond the scope of this class. But they're essentially taking an average, and then they take the square root at the very end to undo kind of squaring out the units. So in this case, if I wanted to find the true standard deviation, which we'll generally label S sub x, I would do this. I already computed the deviations. So I would take all of that, and then I'm going to divide it by number of data minus 1. So in this case, 7. Okay, so I entered all that straight into my calculator, hit enter, and the last thing I'm going to do is take the square root of that. All right, so about 2.27. And they don't give us units here, otherwise I would tack units onto it. But it's a pain to do by hand. You wouldn't want to have to do that. You just want to understand the way that formula works. So I'm going to real quick show you how to do it in your calculator. So let's go back to my calculator screen. I'm going to enter my raw data. So not the deviations that I calculated, but the raw data. So I have 1, 1, 2 2s, 1, 3, 1, 5, 2 6s, 1, 7, and I'm going to enter that into list 1. clear out what I have in here. So I have 1, 1, 2 2s, whoops, not 22. 2, 2. I have a 3, I have a 5, I have 2 6s, and I have a 7. We're just going to go back to doing that stat calc one variable stats again. And so you notice here is S sub x, and there you go. It's that 2.27 that we came up with by hand. So much easier to do in your calculator. You just need to remember that standard deviation is S sub x in your calculator. Okay? Fair enough. Let's move it on. All right, so standard deviation measures the average distance of the observations from their mean, and it's calculated by finding an average of the squared distances and taking the square root. The squared distance is called the variance. This is going to be really important later in the year. So variance equals standard deviation squared, meaning variance is just the standard deviation formula without the square root over it, right? It's mostly important for when we get to combining distributions. It is a measure of spread, although its units don't make sense, really, because the units would be squared units of the original data. So it's just something to remember that the standard deviation squared is the variance. All right. So some properties of standard deviation. I can just kind of review these. We think of it as typical, distance to the mean. It is a measure of spread. It is not a resistant measure. It has the same units as the data itself. Okay? All right, so these are the foot lengths in centimeters for a random sample of 7 14-year-olds from the United Kingdom. Find the standard deviation of this sample. We're not going to do it by hand. We did one by hand, kind of, and that's enough. But we are going to interpret it. So in your calculator, go ahead and enter this data set into list 1 and run your one variable stats. All right, so we see here my standard deviation is about 2.52. I'll say S sub x is approximately 2.52 centimeters. My interpretation would be that the typical foot size in this data set deviates from the mean by about 2.52 centimeters. So it's just a typical deviation from the mean. Always want to make sure that you're discussing it in context, context meaning add units and talk about what the data is representing. All right, so I mentioned this earlier. Now that we have all these different measures of center and spread, you need to choose them carefully when describing a data set. So the median and IQR are usually better than the mean and standard deviation for describing a skewed distribution or a distribution with outliers. That's because of their resistance. Use mean and standard deviation only for reasonably symmetric distributions that don't have outliers. And numerical summaries don't fully describe the shape of a distribution. Always plot your data. So for quantitative data, you should always have some sort of histogram or a box plot to give you a full analysis of your data. The numbers don't tell the whole story. All right, so let's do one more example together. Who has more contacts, males or females? The following data show the number of contacts that a sample of high school students has in their cell phones. What conclusions can we draw and give appropriate evidence to support your answer? So I'm going to go through this one. We're going to make two sets of data. I'll enter male in list 1 and female in list 2. And we can then run one variable stats on each, and we'll plot some parallel box plots to compare. All right, so in our calculator, I'm going to go stat, edit, clear out list 1. Here I'm going to put the male contacts. There we go, and then in list 2, I'll put the female contacts. Oh God, it kicked me out of there. It's looking down at my calculator. Okay, let's try this again. Okay, and they have different amounts of data, but that's okay. We can still make a comparison here. So first thing I'm going to do is run a one variable stats on list 1. This is our males, and I'll make some notes. So the mean is 121.65 contacts. Standard deviation is 74.45 contacts. And then for the female, let's do the same. So I'm just going to quit. I'm going to go stat calc. And I'm going to change the list that I tell it to run to list 2. And so if you have an older calculator, then when you click one variable stats, it should come up with this. Just make sure you tell it list 2. Remember, the shortcuts are just right in front, or sorry, on the numeric pad. You have to use second and then a number 2 for list 2. All right, so I'm going to copy down my mean 126.71, standard deviation 65.75. And then we have all this other, we have the 5-number summary, but I can just use a box plot to represent that 5-number summary. So if we go to second stat plot, I'm going to make sure plot 1 is turned on. It's already selected on the box plot, and that's coming from list 1. Once all that's turned on, I'm going to go back into box plot. I'm going to go to plot 2. I'm going to turn it on at the same time. I'm going to choose a box plot and tell it that I want that data to come from list 2. Okay? And I'll make them kind of opposing colors. Let's do green and magenta. All right, then we can go to zoom, the 9th option, which is zoom stat. We get parallel box plots here. So in this graph that I have, the magenta is the men. Is that right? I believe so. Yeah, the magenta is the men, and the green is the women. And so you can kind of see the median and the quartiles, and we can do a comparison of those if we copy down these box plots. So I'm going to go to kind of the text answer to this, but they do essentially what I would say to do. When you have parallel box plots, you do need to label your categories on the vertical axis. So the way they graphed it, they graphed male on the bottom and female on the top. But your x-axis is the same. So they state the mean, the standard deviation for each, the 5-number summary for each, and then how much data was in each. And then this is the 4-step process that they were referencing earlier. It's state, plan, do, conclude. And it's just a way to, like I said, keep track of everything and describe in enough detail to receive full credit. So state is, what is the problem we're trying to answer? So do males and females differ in the number of contacts they have in their phone? And then the plan is, we'll compute numerical summary and graph parallel box plots to compare shape, center, spread, and outliers. And then do would be, okay, here are the calculations that we made in our calculator. We're listing them out in a table. And here are our parallel box plots. We're listing them in a graph. And now you need to talk about shape, center, spread, outliers. So that's the SOX acronym for both, and compare. And so they said the female distribution is approximately symmetric, but the male distribution is slightly skewed to the right. Center, the median number of contacts for females is a little larger than the median number of contacts for males. Good idea to use medians for comparison because we have some skew here, and the medians, remember, are resistant. Spread, the distribution of contacts for males is more spread out than the distributions of females because the IQR and range are larger. So they do use IQR as, again, a resistant measure to compare. Outliers, neither the distribution has any outliers. And then conclude, so answer your question. Do you think they differ by the number of contacts in your phone? And here's one possible answer. In the sample, females typically have more contacts than males because both the mean and median values are slightly larger. So remember, they're using measures of center to discuss typical data values in that set. However, the differences are so small, so this is not convincing evidence that one gender has more contacts than the other. So basically saying, this could just because of randomness in the sample. There don't seem to be extreme differences between the two. All right, here's your student examples. Go ahead and pause it here and try to answer, these 2 questions. I'll get my face out of the way. And we'll talk about these in the next class.